We all ready?
Dun, dun, dun.
Oops.
No.
What does it say upside down? Yeah, Ria no, or Ribno. Okay, so I have a really half-baked idea today. And so I just want to walk through it. So the goal today is to get to this half-baked, I didn't even want to call it hypothesis. So I said, well, hypothesis / idea. And I don't even understand it myself. So, but I think it was worth just trying to describe it, and maybe I get some feedback about how to think about this. So the goal is to go through a bunch of stuff, that's semi-review, a bunch of questions, and then try to get to this idea.
Is this what Lucas and I erased the other day?
With that question just came up a moment ago, and I said, I don't know because you erased it.
And Jeff doesn't remember.
I don't remember. So it is related to it because I was thinking about different types of representations in the cortical column, different type of SDRs and the meanings of them, but not specifically this stuff. So I'm going to start with like a review of things, but for some of you guys it won't be much of a review, it might still be new things. So I'm just thinking about a single block of cortex, this generic cortex, column if you will, and we can say, okay, what's the goal of a block of cortex, a column of cortex? And the way I like to talk about it, the goal of that thing is it's to learn a model of the world. It gets some input from someplace. It doesn't, if it's generic cortex, it doesn't know what that input represents. It has no idea what it represents. It doesn't know its modality. It doesn't know anything about it, really. This is, here's some input, and I'm trying to build a model of this as it changes. It might change on its own, but also it mostly changes through movement. So we learn a model of the world through movement. So it's basically as the inputs change, as something's moving, and it's trying to figure out the structure of that thing. We know that it's a predictive model, meaning it predicts whatever's the next input, and therefore it must have some copy of the motor command. That's the efferent, EC is efferent's copy, that's a neuroscience term. Effort's copy motor command, so it must know something about the movement, otherwise it couldn't predict what's going to happen. We have struggled with, by the way, understanding, we don't really understand where that motor effort's copy comes from. Where it's not documented, and it's like it's not clear where that shows up here. It's very clear where the input shows up. The input comes from something, it goes to the thalamus and predicts to layer 4, a couple other places too. But this green thing, the motor efference copy, is kind of a mystery. We spent a lot of time talking about that. We do know a lot about the output of this thing, and the goal of this column is not just to learn a model, because what's the point of just learning a model? The purpose in the end is to use that model to create behaviors. And so once you have a model of the world, not only can you predict the future, but you can say, oh, how do I get to a particular state of that model? How do I get to the particular position in space? And actually, I make a distinction between location and state, because things have states. I always talk about my phone. My cell phone has a state, and I want to get to some state, some particular state. I have to do a series of actions to get to some state. Yeah.
Good question. Isn't the thalamic input the efferent's motor copy from the previous?
Well, I didn't draw that here.
Okay.
If I think about a primary motor cortex, a primary sensory cortex.
Yeah, V1 you wouldn't have.
Yeah, but so this is an interesting thing. I purposely didn't talk about the problems of multiple.
Right.
Yeah. So you could argue, yes. Well, you could say if this is another column here, and here's layer 5, then its cells come out and they go into the thalamus of this column, something like that.
Yeah.
But we never really understand that either, because in the primary sensory cortex, that would imply the input from the retina is a motor command. And I've actually spent a lot of time thinking about that, and could it possibly be viewed as a motor command? And so I'm getting closer to that problem here, but I didn't want to address it over here.
Okay. There's also kind of where pathway connections.
Yes.
So the motor cortex projects to.
Yeah, I know, but we've seen projections all over the place. My point is, we don't really understand that. It could be that there's I'm not saying it doesn't exist, we've talked about it. It could be this layer 6 to layer 6 connection we've talked about, which could be the efferent's motor command. It could be, this output through the thalamus. None of these things quite make sense. So I just said to myself, let's just focus on a single column, and let's focus now on like a primary sensory column. So And I just put this here because we just don't really know exactly where it's from. We don't really understand it in detail. We know it has to exist for this column, and I'm going to come back to this a moment later. I didn't really want to focus on that part right now. So again, the goal of all this, we have some movement command, we have some input, we generate a model of this thing has to learn a model of the space that this thing is looking at. It doesn't know what it's looking at, it doesn't know what the world is like. It just says, here's a bunch of bits coming in, and here's a bunch of motor commands, and they're changing, and I have to figure out what is the underlying structure of this thing that I'm observing, and I build a model of it. And we've talked a lot about what that model looks like. The model is going to be built on locations, and I'm not going to go further into that today, but you can just imagine this sort of three-dimensional CAD model of something in the world that says, oh, I've discovered the structure here. But this is very generic because this could be some high-level cortex doing language and not getting sensory input directly. So this is the general idea, and I think you could say generally the purpose of the column is to learn this model and from that create behaviors that allow you to get to some reach a goal, which is some location, some state in the world. And of course, you have lots of columns doing this. Then we can talk about the input to the column here. So you got a bunch of bits coming in that you don't really, this column doesn't know what these bits represent, right? The meaning of these bits, it's just an SDR. I'm talking about this thing right here, this thing that's coming in. It's just some sort of number of bits, some are active, some are not. The meaning of them are unknown, the modality is unknown, doesn't know if this is sound, touch, hearing, some other part of the cortex. The dimensionality of the world that it represents is unknown. For example, often our sensory organs are two-dimensional sensory organs, but those are projections on a three-dimensional space. So my vision is a projection on a three-dimensional space, so is my finger. But we don't, in general, we can't say anything about it. I don't know if the column assumes there's a three-dimensional space and we have two-dimensional projections, or it could assume there's n-dimensional space and some n-dimensional projection on it. That it may be hardwired for three-dimensional spaces. We don't know that. So I'm assuming that we don't know that. And so then we can ask the question, how is this input, which is just a bunch of bits, represented in the cortex? And we have a hypothesis for that. The hypothesis is built on a lot of data, and that's, I call it the spatial polar mini-column hypothesis. Okay, so I'm going to go through that in a moment. But we have an idea like, okay, this input comes in, how are we going to represent it up here in a useful way? We've got a hypothesis for that. We have a bunch of models for that. If you think about the motor output, layer 5, now that's basically these layer 5 cells that project to someplace else in the brain that's motor related. So they never drive muscles directly. They're always projecting some other area that drives the muscles, and that's from the cortex. We can say that it's going to be another sparse distributed representation because everything in the brain is a sparse distributed representation. We can say that I've always said, and I still believe that these cells don't know what they're projecting to. They don't know how to do this. They have to learn how to control the subcortical thing. So this is a generic learning system that says, okay, I have to somehow figure out how to associatively link to these other cells someplace else that are making motor behavior so that I can control them. So that has to be learned. This is not like, oh, this cell goes to this thing and this cell goes to that thing. It's like, no, just a bunch of cells projected some other bunch of cells, and somehow it has to learn to control them. So in general, every region of the cortex, as far as we know, these cells project to some subcortical motor area that then does the actual behaviors. And one of the questions that I've always worried about or thought about is, and we don't really have an answer to this, is what is the form of this motor SDR? How do I think about that? I have a way of thinking about the input. I can say, oh, the input comes in, and I'm going to represent an X. And then I say to myself, well, I know these cells have to control something, but how do I understand them? How do I make these fluid movements? It's like, what do these bits mean? What do the L5 cells represent? It was never really clear to me. So that is like, what is the form of the motor SDR? What do the bits, these L5 cells, mean? Can I put some kind of meaning on them? And then how do they socially link to the subcortical motor areas? So this whole link here is kind of this representation and link was a much poorer formed idea in my mind than the input. The input, I have a clearer sense of what's going on. The output is like, oh, what the hell's going on there? We know what's going on, but how do I think about that? So I was thinking about this problem, and that's what this little discussion is about. Now I want to go through the spatial Pooler minicom hypothesis. This is not new. This is like, okay, we have this input, how are we representing it here? And because I think that's a clue to how we get the output here. So far, so good? Everyone following? Okay. So this is again, and now how do I incorporate it? It would be different. And now I have at least a way of thinking about layer 5 cells to say, yeah, they're a subset of mini columns. They represent what that slice is doing, which way it's moving. And that's a good representation of motor behavior. Movements orthogonal to whatever features I'm detecting. I don't know how to say it better than that. It's kind of a bit fuzzy in my world mind. So I didn't say we don't have efference copy. I'm not saying it's not useful. Maybe all I'm saying is that the cortical column could learn a model of the world without it. It won't be able to predict the future inputs if the behaviors are generated subcortically.
But even more, I think more generally, we have thousands of cortical columns. They're all trying to direct movement.
Yeah.
And from a given cortical column's perspective, it just has a little bit of influence. And so to do prediction, it really needs to know what actually happened. And it's not just subcortical motor structures, it's also all of the other cortical columns that are controlling things.
Yeah.
So this is V4 cortical column, there's V1, V2, and all sorts of things that are trying to control your
Yeah. Well, so
it's like a distributed sense, and I'm giving you a little bit of suggestion, and then now I need to know what actually happened to.
Well, maybe. So I purposely didn't want to talk about multiple columns here, because if you think about multiple columns in a hierarchy, V1, V2, V4, I might come up with something. If I think about multiple columns as not hierarchical, but parallel at different, in the Thousand Brains hypothesis, they're parallel at some point, and representing different slices, big size of the input space. I might come up with a different thing, and there's this huge, we still don't understand how layer 5 cells, how do they become the input to the next column?
I'm saying is that from a particular cortical column's perspective, if it's 100% responsible for the movements, then you don't need the efference copy probably. But if it's only partially responsible, in order to do prediction, you need to know what actually happened.
Well, so let's be careful. So you're right. So this is one of the mysteries of movement. So like a single column might be representing the tip of my finger, and it could represent the motion of that finger in its space. But then when I actually do something, it's this whole complex armature that changes. I was avoiding that question at the moment. I'm trying to tackle one piece of this problem, just one piece, as a way of maybe performing a new basis for figuring out the bigger problem. Like if this hypothesis was right, and I'm far from saying it's right, but what's really suggestive to me is how common complex motion sensitive cells are. That is like they're throughout the cortical column. And why would it be that way? Well, it could be they are representing behaviors. That could be the representation of movement. And the whole system is sensory motor. So I have sensory, and now I have a SDR where it represents that sensory input under this motor position, motor command. That hypothesis gives me a new way of thinking about layer 5, a new way of thinking about various things. And now maybe we can come back later and address, well, why do layer 5 cells project through the thalamus? Or why do they connect in this way? Or how do I represent the broader motor thing? I don't have any answers to those yet. It's just like this is an interesting idea on its own that maybe provides a basis for how to go forward.
Reminds me of this Held and Hind experiment. You remember like the two cats?
Oh, was this the one that was moving and the one that was just in the carriage?
Yeah, it was.
Yeah.
What is that? So there's two cats. They're in identical environments, but they're linked together. Only one of the cat's movements moved the environment. So the other cat, their legs were not allowed to move. Okay. And whenever this cat moved, both environments would rotate the same way.
Literally, they had the cats on two arms on a bar.
Yeah.
And one cat could walk around and turn its body, and whatever that kid did, the other cat saw the same thing.
Yeah, they designed it so the visual input was identical to both cats, but only one cat was responsible for the movement.
Right.
And then they brought up these two cats this way. And then they did a bunch of tests afterward. Like one, in both cases, you saw the same thing, but are you able to do similar tasks? And the cat that was restrained in movement was very limited in what it could do, and things like there were a lot of deficits that it had.
Okay.
So it again suggests that you need to somehow be able to control your movements in order to really learn this.
Well, that is not a surprise anymore for us, right? How could you possibly learn a model of the world?
This would not be predicted by a pure feed-forward model.
No, but
Because
our
you've seen
whole
the same thing about
our
this.
the whole theory, the thousand brains theory and the column theory says the world is a complex structure and you cannot observe it all at once. And therefore, to learn a model of the world, you have to move through the world. And if all you're doing is feed forward stuff, you're not really learning a model of the world, you're learning image classification or pattern classification. But to learn the structure of the world and how to move through the world, you have to move. It's like I can't learn a model of Redwood City by sitting in this room. It's impossible. I have to walk around the city. So the same thing with the cat. If all I see these things flying past me, how am I going to know what's going on? It's like I can't associate my behaviors with, I can't map out my input on some metric space. So we need to have that. I felt there's something. What's really attractive. I'm gonna say it again. What's really attractive to me about this is the idea that there's these. It gives me a way of thinking about representing motor behavior, which I did not have before, and it explains why most of these cells are motion sensitive, which always was a little bit bizarre. And it's basically sort of integrating. If we think about those motion sensitive cells not as like the world is moving on its own most of the time, it's mostly moving because I'm moving, then those are sensory motor representations. And then it's intriguing to think like, why would I want to represent motion as orthogonal movements to the primary slices I've decided? It's like it somehow feels right, but I can't put my finger on why it feels right. It just feels like that's a good way of representing motion. It's like you've already decided, how to divide up this space into a set of bits, and now it's in those features, and those are the features you're observing right now, and that's top ranked features, and now we're seeing how those top ranked features are moving. That seems to make sense. And now we have representation for that. So the SDR of layer 5 cells is, like on our temporal memory hypothesis, the temporal memory is essentially, the SDR is the state of the sequence at that point in time, and the layer 5 cells are the same thing. It's basically the state of this feature in movement in time. It's a subset of the feature representing movement, where the other one's a subset of the feature. The feature in context here is the feature in motion context. How about that way? It's the feature in motion context, where our temporal memory is the feature in pure time-based context. So it's, again, a subset of cells that become active in the mini column representing this particular behavior at this moment in time. So that's it. It's just, I have nothing else to say. It's just trying to make sense of this.
Can I draw one interpretation of
Please do.
this picture of moving orthogonal to a plane? I just wanted to.
Please do.
There's one easy way to draw it, and I'm 50-50 on whether this is what you mean. First, just depict, like, we're talking about like a single mini column, and you like some set of input bits. And let's say this particular mini column, say its feature, just to keep this simple, is going to be these 2 bits. It likes when these 2 bits are active. There are 2 bits there. So say this mini column has this learn feature. So this subset of the input space can be drawn as like a pair of axes, where this is like bit 1, this is bit 2. And right now this mini column's plane and the input space is this. How do we get to that? So because right now there are 4 possible responses for these 2 bits. It could be this, 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 or this.
Yeah.
And when we talk about a plane in terms of neural networks and SVMs and everything, you're talking about like this plane depicts this column's receptive field, because like its response it likes things that are far away from this plane. So right now this cell's
Oh,
favorite.
that's the way you think about it in the, in like a classifier, right?
Yeah.
Or I think of it as those cells are defining a plane, so both bit 1 and bit 2 are on, then the plane goes through that upper right point, because I know this is different. I was confused by this. I was talking to Supertype about this a week ago. It's just my visualization struggles with this idea. You're saying you want to be far away from that plane.
Yeah. So it sounds like you're talking about a vector, and you want to be you want to be far along this vector. Like
Yeah, if that's the way you think about it, it's a vector.
if you're projecting it onto a
Yeah.
vector, that's
Yeah. Okay. All right. Fine. So yeah. So that vector is perpendicular to the plane.
Yeah, it's normal. Yeah, so it's like the normal vector of,
Yeah.
of this plane. So I don't know. In this picture, this view of in this picture, the idea of moving orthogonal to the plane is if the input is moving in this direction. If the input is moving where the bits that are on are turning off, or
Yes.
the bits that
Yeah.
are
So
off
one way to
turning
think about it, if you were not orthogonal, if you were coplanar, then changes would not affect those 2 bits. So other bits could be changing, but those 2 bits are staying on.
Mhm.
So you say I'm still active, and these other things I'm ignoring. So, but if they're changing, that means I'm no longer in the same plane. I'm someplace else, right? And if they both change, then I must be moving orthogonal to the plane, right? If all my bits are changing simultaneously, then that by definition is an orthogonal movement, right? It's to the whole thing.
if all the bits
I'm sorry.
all the bits, maybe if all the bits that this column's paying attention to.
Yes.
Yeah.
Yeah, so I'm looking at 50 bits or 20 bits and say, I respond to this thing. Now, if the world changes, if the other bits are changing and I'm still seeing this and I'm still active, then I would say that there's been no orthogonal movement. But if all of a sudden if half my bits change, well then it's not completely orthogonal, but if all my bits change, then it's orthogonal movement. Is that the same? I think I get difficulty when I think about the plane and where it is. But if we could talk about bits changing, then I would say, well, if my input bits that I'm responding to all change at once, then the movement was orthogonal to my representation.
So it sounds like you're talking when the bits are moving along this line, along this dotted line, when the input, if the current activity is always like this green dot, and this green dot is like moving around, as your input's changing, this green dot is moving around.
Yeah.
When this green dot moves along this black dotted line, that's orthogonal to the.
The problem with that, again, if we're talking binary, that doesn't really make any sense.
No, you're right.
I think I have trouble with that. I'm not sure. I'm not seeing it right or wrong. Or it's just hard for me to think about it that way.
But part of my question here was, are you thinking of these bit spaces? Or when you're talking about planes and input spaces, are you thinking of this types of input space? Or are you thinking of like physical space, like planes in 3D world?
Well, it's tempting to use the physical space as a visual analogy.
As
right.
an analogy, yeah, but are you
When
literally referring to like planes? Like orientation selectivity is just planes in 3D
I'm not
space.
sure. I'm not
I don't
sure.
know if
Maybe I shouldn't use the word plane. I mean, that's my tendency is to think about physical planes that are slicing some 3 dimension. You can think of a plane as a lower dimensional projection in a higher dimensional space. So some dimensions, if you change in some dimensions, it doesn't. My point, the plane. When I was thinking about this, and maybe I'm using it incorrectly, I was thinking about this mini column represents a plane. What I mean by that is the same mini column responds exactly the same, where some of the bits that it's not paying attention can change. It doesn't affect it. But if the bits that are, and so that's like, those are movements orthogonal to the plane, or orthogonal to the representation. Any changes in these bits here don't change this mini column per se, as long as this mini column stays active. And then you say, okay, well, those are orthogonal movements. But here's another thing to think about it. It's not just any change here. Remember, the complex cells, we're saying, where the complex cell idea comes along? The complex cell idea says, these are patterns that you typically observe in time. It's like a temporal pooling operation. It says, this is equal to this, is equal to this, is equal to this, is equal to this, only because I've observed them in time. That's the assumption. I observed this pattern followed by this pattern followed by this pattern, this pattern. Either way, that's how I represent a complex cell. It's not some inherent property of the space. And now, given I've done some temporal pooling that says these are equivalent, now I can further subdivide and say, well, there's movements in this way and there's movements in this way. I'm subdivided there. So I guess I'm having really trouble on using the word plane. That's why I said slice, plain quotes. I don't know, Marcus. It's confusing to me. So and you guys think about planes differently. You're thinking in the SVM or the.
Can I ask a question about the complex cells? If I remember correctly, the grouping of the orientations is usually still somewhat localized. It's not a single feature, but it's still localized in the visual field. I mean, the human Weasel thing, when they generalize, they talk about hypercomplex, where it says, yeah, I see that orientation anywhere in the visual field. That was an abstraction. But don't those
Well, it's over a small area.
but it's over a small area.
Yeah.
So,
Not anywhere in the visual field. It's over a small area.
Right,
Yeah.
right. But you could imagine if you were pooling the outputs of that to a higher level, then you could say there's some motion anywhere in the visual field.
Well, all you can say is those things are equivalent. That's a complex cell, right? A complex cell says, I respond independent of where this feature is. It's the same feature, but it's anywhere in this range.
Right, but you still have some notion of locality, but if you wanted to.
If you did the temporal pooling over that, then you'd have a broader sense of locality, right? It would be less specific.
Right.
Yeah.
So you have some notion, there is some motion in this particular area of the visual field.
It doesn't tell me there's motion. The complex cell just says this feature exists anywhere in this visual field. Only when I get to the motion sensitive complex cells can I say there's motion. At that point, one moment I give you the vertical line on the left, and an hour later I give you the vertical line on the right, and the same cell's going to respond.
I see what you're
So there's no implied motion at that point. There's applied equivalence.
Okay.
Right, I assume what they're saying, that's like your max pooling operation, right? There's no motion in the max pooling operation, it's just a temporal pooling operation, just simple temporal pooling operation says these are equivalent.
Right, but it also means that you, if you wish, detect motion aside, you detect that feature with some spatial invariance. In other words, I see this feature, and I don't have to be right precise on this thing, I can be a little bit over, so that gives you, if you wish, a soft variation.
Yeah, that's your max pooling, I guess.
Right. So if you imagine where you're looking at these things where these cortical columns exist such that you have the orientation slightly tilted on the kind of adjacent ones, you have this thing that you go around.
The orientation progresses as you move across.
Right. So that gives you a softness in orientation too, if you pool from there too, right?
Yeah, but I don't know if there's any evidence for that. You would if you pull from that. If you pull from that, then you're back to where you started from. Then basically everything gets pooled together.
Well, I'm saying, not everything. I'm just saying if you have selective pooling, then you basically, if you're saying, yeah, the example you gave up there where you had, it's perfectly vertical, but the other orientations kind of get this little bit of excitation.
Yeah.
So you get a little softness there, which
You
is
do.
actually good. It's noise immunity.
Yeah, it's noise immunity.
Yeah.
But you don't pool over all of them, because then you go into that, right?
No,
Yeah.
I didn't mean that. You
So-
still need to be.
So what it's basically, another way of interpreting it, as opposed to noise immunity, you could say these features aren't binary.
Right.
There is a small level of gradation or scale to them.
Softness to them. Yeah.
Well, softness, but I would rather call it scale. It's like, how vertical is this? Well, it's really vertical or mostly vertical, and then not enough to be count, So maybe think about it as 2 bits of precision or something like that.
Okay.
Right? That's what it appears to be in the cortex. We abstracted that to purely binary just because it's easier, and it seemed to work pretty well. So we didn't go back yet, but we know that it's not true in the brain.
Well,
Yeah, but even if there's different response rates, I think a lot of the impact is still binary.
Yeah, I agree. The power comes from the distributed representation,
Yeah.
not from the scale part of it.
Yeah, because the scalar part, you still have to average over a second to get the firing rates, and the response, the impact on a postsynaptic cell is going to be on a very small
Yeah,
fraction.
exactly,
So it's
right.
the coincidence of inputs more than.
That was one of the observations that drove our theory, is that, as soon as I point out, you can do all this really complex stuff in a single spike. They're not atomic two spikes. Therefore, there can't be any gradation.
But you,
You could think of it as binary.
but you can do coincidence detection.
Yeah, that's the distributed nature.
Right,
You get the coincidence of things.
So the plane concept is a very crisp notion. And
Well, is it? We were struggling with it. I don't find it crisp at all. I'm really struggling with it.
It's crisp in the sense that if you know, the definition in some sense is if you have a vector that's representing the synapses of that cell, and you have a vector representing the input, if the dot product is greater than some threshold, that defines a plane.
Right.
In some sense.
I was even struggling to say
You
this.
could do that in binary too, so in that sense it's a plane.
But when you do it in binary, the concept of the visual input of
Yeah, the visual stuff
doesn't
work.
make any sense. And then we have to. This is where we have to define a plane more mathematically, because the idea of this sort of physical plane going through space makes no sense in a binary world.
I'm just wondering if it's any one particular one is binary, but you would want to cool these things to some degree so that you can, so it's not that crisp.
When you say cool them,
In other words, you know,
what?
the cortical columns being the adjacent ones saying, yeah, I got some response. So you could improve the both noise immunity and the ability to detect that finer gradations. In other words,
Yeah,
it's hard binary solid.
I think that's a more important point. As Pivotal was pointing out earlier, if you have a distributed representation, so it's not one bit that you're looking at 50 bits that are on, then the individual quantization noise of any particular bit is not going to be very important.
Yeah, exactly.
Right, but what it would do is it would allow you to, in some sense, represent sub-quantal states, if you wanted to say that. But I think we've chosen up to now to try to ignore that as much as possible. That really complicates things. And if you think about it as binary, until we can't anymore. But if you think about binary, it simplifies things tremendously. And if it still works, then we say, okay, we'll come back to the fact that it's not exactly binary in the future.
Okay.
We saw this. We really started running up against this for the first time when we were talking about grid cells. And where in grid cells we ran into some hard boundaries in terms of like you can't get away with pure binary, you know. I can't remember exactly how we got that, but we got to that point where you had some real convoluted arguments that were not
I mean, in one sentence, anytime you want to integrate some continuous variable, the keyword integrating. When you're integrating some variable, you want something like a graded response.
Yeah. So we'll get to that eventually. I'm hoping that all the arguments I made here today are independent of that completely. They're really more about the nature of the representation. Just like the spatial pooler is just a representation of the input space that we can get our heads around, we can understand what it means, we can manipulate it and work with it. This idea gives me a representation of a motor command, which is derived from the minicom, which is tied to the minicom, which was really what Mountcastle's hypothesis was. That the minicom is the unit of processing. So now I can say, oh, each minicom can define its own bit of sensory input and its own bits of motor output, and the set of them represents something meaningful. So that you can do independent of whether the minicoms are slightly overlapping or binary. I think the same intuitions can be understood in both those cases.
I guess the thing with the binary is that my intuition says is that will be subpernal.
Maybe what? It's not as good as you think because of the distributed nature.
Yeah.
Well, no, I mean the distributed nature overcomes the fact that it's binary.
Well, that's the point.
But then you're saying, you know, you still have to have a representation of it.
The representation is the distributed representation, right?
Okay.
Remember, another way to think about it, not only do we do things in a single spike, but we do things with great loss. So the system is very robust to the stochastic nature of the neurons and the cells. So, you know, lots of observation has been that individual synapses and neurons are not very reliable, and our system is reliable. Therefore, it basically, that moves you away from this sort of very high resolution neural network type of thought to more this binary, more binary-like representations.
But if it's distributed, then you also have to bring it back in. You have to have pooling in order to make sense of that distribution, right? In order to
It's
get
not
some
pooling,
kind
you don't have to pooling, you just have to always look at the distributed representation. Everything is, no neuron ever can be interpreted completely on its own. It always has to be in a distribution. So if I go from SDR to SDR to SDR, then I don't necessarily have to have pooling. It's just that's the way it is. It's just SDRs and bulk SDRs. And at any point in time, I can drop out any number of those bits along the way, and the whole system keeps working. Even 40% of the bits can be dropped out, and the whole system keeps working.
Okay, on one of these dendritic branches where you say 20 up to 5, you're inherently pooling at that point.
I wouldn't use the word pooling for that. That's not how I would use the word pooling. Pooling is, that's different for me. That's a different use of the word. So that may be the problem here. You're using the word differently than I use it.
Okay.
Pooling to me is you have multiple SDRs that get converted into a single SDR. So that's pooling. Multiple input SDRs get mapped to a single spatial pool output SDR, or multiple input SDRs get mapped over time through the temporal memory into a single output name of a melody versus the notes of the melody.
And that's anathema to you?
What's that?
That's anathema to you to have that assumption?
No, it's built into the system. Everything, the spatial pooler and temporal pooler are basically the whole idea is that you're doing that kind of pooling. But I wouldn't say the 20 bits on a dendritic segment aren't doing that. That's something different. They're not pooling multiple SDR. In the sense of doing spatial pooling, if you want to consider it that way.
Yeah.
Okay, well, fine. Then they're doing spatial pooling in the same sense as the mini
There's
column.
a temporal component too. They all have to, some percentage
That would be
have to
temporal
fire.
pooling. They're not doing temporal pooling. Temporal pooling means that one SDR and another SDR that occurs over time, which are completely orthogonal SDRs, they don't have no overlaps bits, get converted into the same output. And the dendritic segments, we don't have them doing that. The dendritic segments say, I just recognize a single pattern, and they don't pool on that segment. The same dendritic segment doesn't a moment later represent a completely different SDR.
All right.
So I guess if you're saying, do the dendritic segments exhibit a spatial pooling type of operation similar to how the mini columns do? Yes, I would agree with that. But we don't.
But there's no inhibition.
There's no inhibition. There's no
It's just-
boosting. It's just it's missing some of the attributes of the spatial pooling. I mean, that's why we call it spatial pooling and temporal pooling, because of pooling operations. It's a bit tricky to get. Half the time the language is important. Anyway, we can end here. I know you guys have a lot to do. The thing I would need help with is really coming up with a visual metaphor and the usage of the term for planes or slices, or is it a vector? This is where I'm confused. I'm thinking about planes or something else, and so maybe that would be helpful for me to get some more insight on that. That's it. That's today's ideas, unless someone wants to ask more questions about it. All right, going once, going twice.